Look up at the night sky. What do you see? Thousands of twinkling points of light. Each one is a star, a giant ball of burning gas that emits light and heat. For millennia, humans have gazed at the stars in awe and wonder. They have inspired countless myths, legends, and scientific discoveries. Stars are not just beautiful, they are the building blocks of galaxies and the crucibles where heavy elements are forged. Our very existence is intimately connected to the life and death of stars. The universe is filled with these celestial wonders, each with its own story to tell. Some stars are massive and short-lived, while others are small and burn for billions of years. Some stars exist in isolation, while others are locked in a cosmic dance with companion stars. In this exploration, we will delve into the fascinating world of stars, from their birth in interstellar clouds to their eventual demise. Stars are born in vast cold clouds of gas and dust known as nebulae. These nebulae, often called stellar nurseries, are scattered throughout galaxies. They are composed mostly of hydrogen and helium, the two most abundant elements in the universe. These clouds can be light years across, containing enough material to form thousands or even millions of stars. One famous example is the Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of the constellation Orion. This stellar nursery is a hotbed of star formation, with new stars igniting within its depths. Within these nebulae, gravity plays a crucial role in bringing the scattered gas and dust together. Over millions of years, gravity draws these particles towards each other, causing the cloud to fragment and collapse. As these fragments contract, they heat up, becoming denser and more compact. As each fragment of the nebula collapses under its own gravity, the particles within it collide more frequently. This collision generates heat, causing the temperature at the center of the collapsing cloud to rise dramatically. This hot, dense core is known as a protostar. It is the embryonic stage of a star's life. The protostar continues to grow, pulling in more and more gas and dust from its surroundings. As it gains mass, its gravitational pull strengthens, accelerating the process. The infalling material forms a swirling disk of gas and dust around the protostar, known as an accretion disk. This disk provides a steady stream of material that feeds the growing protostar. The protostar's core continues to heat up under the immense pressure of gravity. Eventually, the temperature and pressure at the core become so intense that a remarkable process ignites nuclear fusion. Nuclear fusion is the process where lighter atomic nuclei combine to form heavier nuclei, releasing tremendous amounts of energy in the process. In the case of stars, hydrogen nuclei fuse to form helium. This fusion reaction is what powers a star. The energy released from fusion creates an outward pressure that counteracts the inward pull of gravity. A delicate balance is achieved between these two opposing forces. This balance, known as hydrostatic equilibrium, marks the birth of a star. The protostar has now become a main sequence star. Section 5. The main sequence, stellar adulthood. Once a star achieves hydrostatic equilibrium and begins fusing hydrogen in its core, it enters a long, stable period known as the main sequence. This is the longest stage in a star's life, and it is during this time that it shines brightly, steadily converting hydrogen to helium in its core. Our own sun is a main sequence star about halfway through its estimated 10 billion year lifespan on the main sequence. The color and luminosity of a main sequence star depend on its mass. Massive stars are hotter and brighter, emitting bluish-white light. They burn through their hydrogen fuel much faster than their smaller counterparts. Less massive stars are cooler and dimmer, emitting reddish light. They burn their fuel much more slowly, allowing them to live for billions or even trillions of years. Section 6. Red giant stars in their twilight years. As a star ages, it gradually exhausts the hydrogen fuel in its core. Eventually, the core is primarily composed of helium, and fusion slows down. As the outward pressure from fusion decreases, gravity begins to take over. The core contracts and heats up, causing the star's outer layers to expand dramatically. The star swells to an enormous size, becoming a red giant. Red giants are much cooler than their main sequence counterparts, hence their reddish appearance. However, they are incredibly luminous due to their enormous surface area. During this red giant phase, the star's core continues to contract and heat up, reaching temperatures high enough to initiate the fusion of helium into heavier elements like carbon and oxygen. Section 7. Stellar corpses, white dwarfs, neutron stars and black holes. The fate of a star after its red giant phase depends on its mass. Low-mass stars like our Sun eventually shed their outer layers into space, forming beautiful planetary nebulae. The exposed core, now a dense hot ball of mostly carbon and oxygen, is called a white dwarf. White dwarfs are incredibly dense, with a mass comparable to the Sun packed into a volume roughly the size of Earth. Over billions of years, white dwarfs cool down and fade away, eventually becoming invisible. More massive stars, however, meet a more dramatic end. Their cores collapse so violently that they trigger a supernova explosion, one of the most energetic events in the universe. Section 8. Supernovae, the spectacular deaths of massive stars. When a massive star exhausts its nuclear fuel, its core collapses under its own gravity. This collapse happens so rapidly that the core rebounds outwards, creating a shock wave that rips the star apart in a cataclysmic explosion known as a supernova. Supernovae are among the brightest events in the universe, often outshining entire galaxies for a brief period. They are essential for cosmic evolution because they disperse heavy elements forged in the star's core into space. These elements eventually become incorporated into new stars, planets, and even life. The remnants of the supernova explosion depend on the mass of the original star. For stars several times the mass of the Sun, the core collapses to form an incredibly dense object called a neutron star. Neutron stars are only a few miles across but can have a mass greater than the Sun. They are composed almost entirely of neutrons, subatomic particles with no electrical charge. For the most massive stars, the core collapses indefinitely, forming a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Section 9. Our place in the cosmic ballet. The life and death of stars is a continuous cycle of cosmic creation and destruction. The elements that make up our bodies, the Earth, and everything around us were forged in the hearts of stars billions of years ago. We are literally made of star stuff. Understanding the life cycle of stars allows us to trace our origins back to the Big Bang and the formation of the first stars. It helps us to comprehend the vastness and complexity of the universe and our place within it. So, the next time you look up at the night sky, remember that you are witnessing a cosmic dance, a symphony of light and energy that has been playing out for billions of years. Each star is a testament to the grandeur and wonder of the universe we inhabit.